This lesson is about roots of complex numbers. The first part will walk us through a discovery from about 400 years ago that will be pretty useful when we get to the problem solving part 2 of this video. Consider this equation. X to the third power is 64. That means some number to the third power is 64. And an obvious answer to this equation is 4. And you could find that either by guess and check if it seems obvious to you, or you may have learned to cube root both sides, which effectively leads to the same answer of 4. Mathematicians have long known that equations with cubes in them, or third-degree equations, have 3 solutions. And 4 seems to be the only noticeable answer to this equation on first glance. So what mathematicians did is they decided to set the equation equal to 0 and use an old factoring trick to see if they could find the other 2 solutions. You may not remember this kind of factoring. It's obscure and you don't hear much about it, but don't let that be the focus of the video, because this is not the algebra we're going to be using ultimately to solve these, but this is what they did. And by setting each factor to 0 using the zero product property, the first answer they got was the obvious one that they already knew, which is that x would be 4. But from the second equation, the quadratic equation was used, and that led them to 2 more answers for a total of 3 answers. When they applied the quadratic formula, they got a negative under the radical. That, of course, led to an imaginary number. And after some more simplification, and I wouldn't worry about the details here, it's not the main point. The idea being, however, that after some simplification, there were 2 more solutions to this equation, and they had found all 3 that they had anticipated finding. Well, for whatever reason, curiosity, I'm sure, they decided to graph those solutions as we would graph complex numbers ordinarily in the plane. And what they discovered when they graphed those 2 solutions, along with the solution that they knew, 4 or 4 plus 0i, is that some interesting things came to light. The first thing that was noticed is that all of these points, these complex numbers, which they call the cube roots of 64, were all the same distance from the origin. More generally stated, they had the same modulus. But they noticed something else. They noticed that the angle between the solutions was the same all the way around, and in some sense these solutions were evenly spaced around the circle. Mathematicians then went on to prove that this not only happens for cubic equations, but any other 4th root, 5th root, or higher, and it would happen all the time. In other words, they proved that this was not just a coincidence, but that it was more generalizable. And we're going to use that generalization in solving our problems today. Now, one could argue that the algebra that led to the solutions of these problems, as you can see here, isn't all that bad. It's a little annoying. But even if you're willing to do this kind of algebra, it's not a guarantee that you'll be able to find any root of any number by this process, because this process will work under certain circumstances and not under others. And so mathematicians needed a way to solve roots of complex numbers without relying on algebra, which, as I said, worked when it worked and didn't work when it didn't. So we're going to look at this problem a different way. If we wanted to find the cube roots of 64, the first thing we would do is notice the obvious one, which is 4. And then we could plot that in the complex plane. But then, knowing that all the solutions to this equation have to have the same modulus, we know that our other solutions are going to lie on this circle of radius 4. And furthermore, knowing that they're evenly spaced out, tells us exactly where the other two solutions are. And so what we could do is express these in polar form and essentially have our three answers to this equation right here. Although it is not the norm to answer in polar form, it's sort of more traditional to answer in rectangular form. So what you could do with these polar answers is convert them to rectangular. That is a whole subject unto itself, which I've made a video on. If you're uncomfortable with that, I would back up and check out the video called Complex Numbers, Polar, and Rectangular. But assuming that you've mastered that skill, let's use that and move on. I want to take a look at one of the answers in particular of the three that we had, and I chose this one randomly for no particular reason other than to pose the following question. I've allegedly found a cube root of 64. Doesn't that mean that if I cube this, I should get 64? Well, how could something so ugly being cubed simplify all the way down to 64? Well, just to prove that it did, I labored through all of the algebra here, raising this thing to the third power, using FOIL, using the fact that I squared is -1, and all kinds of other simplification. And at the very end of it all, after some cancellation, this thing actually did equal 64. If you were to pause the video right now and check the math on this page, you'd find out that it actually works. But let's not worry about the particular details, because this is not algebra that you're likely to have to go through. But I thought it was worth showing that the thing that we found claiming to be a cube root of 64, when cubed, actually was 64. Now let's look at some specific examples. Suppose we wanted to solve x cubed equals 8i. Well, we've got to find one solution so that we can use that to generate the other ones, being evenly spaced around a circle. On first glance, you might think that 2 is a solution. After all, 2 cubed is 8. You might then think that 2i is a solution, but it turns out if you cube 2i, you don't get 8i. It's not how complex numbers work. So we're going to go a slightly different route to find a solution here. We're going to convert this into a polar complex number. I'm going to take the number 8i and write it as 8, 90 degrees. And once you've converted to polar, you can make use of some good shortcuts that will get us to a solution here. Now, x is some complex number, and we don't know what it is. But we know it has a modulus and an argument, so we could call that modulus r and the argument theta. So I've got r theta to the third power equaling 8, 90. Here is where de Moivre's theorem comes in handy. You'll recall that de Moivre's theorem allows us essentially to distribute the exponent in the way shown here. And now I can deduce that if I'm looking for a specific r and theta to make this true, I could set the first coordinates equal to each other and the second coordinates equal to each other as well. And these two equations are easily solved by just looking at them. And now we know that r can be 2 and theta can be 30 degrees. Now, by the way, there is a slight comment that needs to be made here. Just because polar complex numbers are equal to each other doesn't necessarily mean that their individual components are. For example, here's two complex numbers that are equal to each other if you think about where they are in the complex plane, but clearly the two arguments are expressed in different ways. That's a slightly elusive piece of logic there that you technically don't need for this problem, but suffice it to say that the r and theta that we've found here are not unique. There are other r's and thetas that would work. But remember, we only need one solution to this problem to then deduce that the other solutions are spread around the circle, so 1 is good enough for now. And let's look where that solution is. That solution is 2 spaces away from the origin at an angle of 30 degrees. That is one possible cube root of 8i. But let's recall the discovery from the 17th century. We know that when taking roots of a complex number, that they're all going to have the same modulus and be evenly spaced. That means my other roots have to lie on this circle of radius 2, and because they're evenly spaced throughout the circle, they have to be in the locations indicated by the red dots. And furthermore, if you break up a circle into 3 equal arcs, each one of them would be 120 degrees, which tells me that this angle here is 120. And now that I know that angle is 120, I can take my 30-degree argument from the first solution, add 120 degrees to that, and then add 120 degrees to that to get the other 2 solutions. Now what I have here are the 3 cube roots of 8i. However, they're not in rectangular form, which is the traditional answer format. So, using your conversion skills, you will eventually have these in rectangular form and thus have your 3 cube roots of 8i. Let's take a look at a problem that involves fourth roots. In solving x to the fourth equals negative 16, it would greatly simplify the algebra to express negative 16 in polar form. And by doing that, I can rewrite x using its modulus and argument, and with the fourth power, I can apply de Moivre's theorem. This again enables me to find a possible solution for r and theta by setting the first coordinates equal to each other and likewise the second coordinates equal to each other. And again, it's worth saying here briefly that because complex numbers can be equal to each other even when the components themselves are not, in other words, because complex numbers in polar form can be expressed in more than one way, I can't claim to have found all the values of r and theta that will make these two complex numbers equal to each other, but it doesn't matter because I simply need to find one of them so I can use that as a basis for my other fourth roots of negative 16. So plotting the point that's 2 spaces from the origin at a 45-degree angle tells me where one of my fourth roots is. But again, as discoveries have shown, all of the fourth roots of negative 16 must have the same modulus. That means they all lie on this circle of radius 2. And again, because they're evenly spaced, I know where the other ones are. After all, if you divide a 360-degree revolution into 4 equal parts, there should be a 90-degree spacing between answers, and that's exactly what I have here. I have my fourth roots all 90 degrees apart from one another. And therefore, since one of them has an argument of 45, I can add 90 to that, add 90 to that, and add 90 to that, and have all 4 of my fourth roots. So in one sense, I'm done with this problem. There are the 4 fourth roots of negative 16, but again, as tradition would have, we like to express our solutions in rectangular form whenever possible. So, using the conversion skills that you've picked up in other courses or videos, you can convert your polar complex numbers into rectangular ones, and there are your 4 fourth roots of negative 16. Now, I didn't take the time to show the algebra here, but if I were to pick any one of those, raise it to the 4th power, and do all of the messy work that would follow, the result definitely would be negative 16. And for our last problem, let's take a look at a fifth root. To solve this equation, I will do much of what I did in the previous problem. I'll express the right side in polar form, rewrite x in its component format, apply de Moivre's theorem, and make equations that will find one pair of possible values for r and theta. Again, this doesn't find all of them, but I don't need all of them. And now that I know one of my fifth roots is one space away from the origin at a 0-degree angle, I know that it's right there on the positive x-axis. Now before we go any further, I'd like to mention that all of the algebra that you see above probably wasn't necessary. Even though that's the same technique I used on the prior two problems, I wouldn't bother with all that on a problem where you can see an answer in a more obvious way. Look at the original equation. I think we could all agree that 1 is a solution to this problem because 1 to the fifth is 1. If you know that 1 is a solution to this problem, then you know that one of the solutions lies on where the red dot is. And that's really all we need to know to proceed and find the other 4 of our fifth roots. Again, we know that they have to have the same modulus, which means that they lie on this circle of radius 1, and we know that they're evenly spaced. What does evenly spaced mean here? Well, if you divide the circle into 5 equal parts, each of these angles here is 72 degrees. Therefore, knowing that one of my solutions is at a 0-degree angle, I can add 72 to that, add 72, add 72, and add 72 one more time to get all 5 fifth roots in polar form. All I have to do now, as is typically the case, is convert those to rectangular form, and I'm done. The one minor peculiarity of this problem, though, is that we can't convert these to rectangular form exactly because there's nothing about the angle of 72 degrees that lends itself to exact answers. So, using sines and cosines and all of the angles here, I was eventually able to convert these, but in decimal format and not exact format using radicals as you saw in the previous problems. Nonetheless, there are my 5 fifth roots of 1. And while I am done with this problem, there is a little bit of vocabulary I'd like to end with here. Whenever this number on the right side of your equation is a 1, which is actually quite often, when that number is a 1, this circle down here is, of course, going to be the unit circle. And when we have our roots on the unit circle, we say that we have found the roots of unity. And in this case, because these are the fifth roots of unity, we refer to them that way. And that concludes the lesson.